All right, guys. I want to pick up where we left off yesterday. Remembering that when we're dealing with the unit circle, okay, the arc that we are tracing out when we create an angle. So, for instance, that arc right there, okay, that blue arc, A to A prime, has a length of pi over 6, right? Okay, pi over 6 units. The angle that is the central angle there is exactly the same radians, pi over 6 radians, okay, which we can convert to 30 degrees if we want to. So this, and I'll post this on my website. I think it's one of the better unit circle ones I've created, where it's showing you when to change the angle, and right now it's set up to change by increments of 15, which is pretty much going to address almost every angle that we have to deal with throughout the course. So you get pi over 12, pi over 6, pi over 4, that kind of thing. So it's giving you the angle measurement up here on the slider, but it's also giving you that angle in radians right here in blue. Is that right? Okay. Now it's also at the same time providing you the exact ordered pairs of some of these angles. Now the pi over 12 multiples. Now some of the pi over 12, like pi over 12 times 2 is 30 degrees, right? Or pi over 6. But some of like the 15 degree, 75 degree, 105 degree, those are going to give you those nasty decimals, which we will actually have better ways of dealing with those when we get to other chapters in the course. If you want to take your stuff in the desk in the hallway, it'll be quieter out there for you, and it should be open and everything good. If you got questions, just come in and ask. So we've got this relationship here that what we've been calling T, which is the blue distance, is equal to theta, which is this angle on the interior here. Okay. What we're going to get at, guys, is we're going to be interested in asking, okay, well, if T is all the way out there at 150 degrees, or because we're using the distance, it's always going to be in the radians, it's the 5 pi over 6 measurement, we want to figure out what the ordered pair of A prime is. Okay? Now, the ordered pair of A prime is going to be very similar to the ordered pair that A prime is right there. Okay? If I look at that A prime and we figure out what its ordered pair is, if I take that information, come on, that angle, that segment, that arc, and I reflect them across there, okay, across the y-axis, is A prime and A double prime sub 1, are those going to have very similar ordered pairs? Yeah, okay, because of the symmetry in the y-axis there, right? What is the only thing that's going to be different about those ordered pairs? The signs, the SIGNs, right? Okay, now so you're going to hear me say that a lot because working with geometry, trigonometry, we're interested in SINE, that sign, which is going to be the y value of these ordered pairs, and the SIGN, which is the plus or minus of the x values and the y values, right? So a lot of times you're going to hear me spell out sign, okay, if I want SIGN. So yeah, the y value of A prime and A double prime should be the same thing, right? The x value going from B to A prime, that x value should be the same length as going from B prime to A double prime sub 1. But what direction did I go from B to get to that point? I went left, so that shouldn't that ordered pair be negative? Does that make sense, everybody? So if I show that ordered pair there, and then I kind of commit that to memory, radical 302, 1/2, come over here, negative radical 3 over 2, comma 1/2. Same value, same quantities, but the x is now negative, right? Does that make sense, everybody? Okay. So when I'm asked what is the terminal point, because that's what we're going to be interested in, so that's the coordinate of this point here. A prime is our terminal point. It's the coordinates of that, and they're associated with 5 pi over 6. The process for doing this, guys, the process for figuring this out is to first find what we call a reference number. Okay? If you go back to chapter 5, it's analogous to what we talked about as the reference angle. Okay? The reference number is talking about the distance, though. So the reference number would be how large or how long that arc right there is. Okay? So because we call the blue arc T, we would call the red one T bar. Is that all right? The reference angle back to chapter 5 would be that angle right there. Remember calling that theta bar? But because we're in radius, we're in the unit circle, those two things should be equal. So however you want to view it and think about it, it's up to you. I don't care. I like to think about it as the angle. That's just the way I was taught. This textbook uses this terminal point in the arc length, which is fine. But we got to figure out how big that is. Okay, so the blue arc is a length of 5 pi over 6. If I go from A all the way through over here to this point, let's just call that point C, how far have I traveled? I've traveled pi units, right? Does that make sense? Okay. Or if I think about this blue angle getting traced out all the way from my initial ray being the positive x-axis, my terminal ray being the negative x-axis, that would be an angle of pi radians, right? Okay. Now, what I like to do, because this point here, or point out this value, this distance, was in a denominator of 6, so we're in sixes, I like to rewrite pi so it is in sixes. Because now it's kind of easy to see if the blue distance was 5 pi over 6. How much further do I need to get, or do I need to go to get to 6 pi over 6? Pi over 6. So pi over 6 is what we call our reference number. Okay? Now I call it a reference number because it's that distance, right? Chapter 5 talks about that as being your reference angle. However you want to think about it. They're the same. Okay? Okay, so now how does that help me? Well, a reference means that I'm going to look something up, right? I'm going to go to the reference section of the library. I'm going to look up things out of dictionaries, out of encyclopedias, out of atlases, that kind of thing, right? Those are the books that are in the reference. And it's going to tell me something about my concept or my whatever I'm interested in. Does that make sense? So here, I'm going to reference, I'm going to look up what 5 pi over 6's terminal point is by referencing or by looking at pi over 6. Okay? So pi over 6 had a terminal point pi over 6 had a terminal point of radical 3 over 2, comma 1/2. Okay? So 5 pi over 6 is going to have the exact same order pair. So 5 pi over 6 terminal point is radical 3 over 2, comma 1/2. That's the reference aspect. Okay? You're looking up to see what ordered pair you have. But now I have to adjust it, because what quadrant did 5 pi over 6 rest in? Or what quadrant did it terminate in? The second quadrant. So what are all the x values in the second quadrant? They're all negative, right? So I need to put that negative in there in my terminal point, and now I know that 5 pi over 6 has that ordered pair, negative radical 3 over 2, comma 1/2. Okay? Now the reason we're going to do this, grab your calculator real quick. Put it in radian mode. I'm just going to have you do radians because that's what's, you know, up there, but the same thing happens if we're in degrees. We just have to be able to convert the radians that we're using into degrees. Type in cosine of 5 pi over 6. Your calculator gives you back negative 0.86 something, right? Okay. Now, your calculator doesn't have the ability to write that as a exact value. What's the exact value for negative 0.866, whatever they give you? Negative radical 3 over 2. Okay. Type in type in sine of 5 pi over 6. Get 1/2? Okay. And that's the y value that's coming out of that terminal point. Does that make sense to everybody? So these terminal points are telling you how the sine and cosine are evaluated at those angle measurements of 5 pi over 6. When we do any one of, you know, there's a lot of angle measurements up there that we're going to be interested in. That's kind of the procedure. Okay. So let's do a couple more of these. The one thing that I hope that we understand or that we see is when I'm in the first quadrant, okay, that information right there comes from looking at give me a minute to create this. What kind of triangle is that yellow triangle there? It's a 30, 60, 90 right triangle. That's a right angle right here. So this information here, because we know that our radius here, how long is that radius? It's 1, right? Because we know the radius in a unit circle is 1, we know that we can find distance B to C. B to C's length is 0.866, which is radical 3 over 2, right? Now I got rounded to 2 decimal places. And C to A prime's length is 0.5, right? Okay. Well, when I move this to, so that's where that order pair comes from, is using that 30, 60, 90 triangle in the ratios that exist in the 30, 60, 90 triangle. When I change it to a 45, 45, 90 triangle, okay, this distance is, this x distance is radical 2 over 2, this y distance is radical 2 over 2, and that's how we get that point A prime, right? There's your 30, 60, 90 triangle again. It just flip-flops the 1/2 and the radical 3 over 2. All right, so then when I come over here, do I still have, it's 120 degrees to this radius here, but is this still then 60 degrees? That's still 90, and that's still 30? So do we see we still have this 30, 60, 90 triangle here with these two values? And that's why this coordinate right here, we're moving left. Now, length is going to show up as a positive number, but we want the direction because it's the ordered pair. So we went left, so it's negative 1/2, and then we go up, so it's radical 3 over 2, right? So all of these values that exist on the unit circle here are coming from those 30, 60, 90 triangles, okay? Now, we do have occasionally, like right here, okay, we have a 15, 90, 75 triangle, which isn't a really nice, convenient triangle to work with, but we do get that 0.9659 number, which, kind of going off memory real quick, I think it's radical, let me check real quick, radical 2 plus radical 6 divided by 4, yes. Okay, so that order for that x coordinate for that point right there, and we'll figure this out. This is what part of our course is about, is trying to figure out, well, okay, what is the order pair for a 15-degree angle? It's going to be radical 6 plus radical 2 over 4 is the x coordinate. Okay, it's messy, but It's true, and it's the exact value. And we can do the same thing for the y coordinate to find that 0.258. That's kind of where we'll take some of this stuff. And we can actually find that by taking the 45 information, the 30 information, running that through a formula, and it will give me the 15-degree information. Does that make sense? Okay? So that's kind of what trigonometry is about. But we get these triangles. Okay? Now, if I understand what that triangle there is, what that triangle there is, what that one there is, through symmetry, okay, is this triangle here the same as that one? Is that triangle the same as the one on the left? Is that one on the right the same as the one on the left? So we can use symmetry. If I know these essentially 3 triangles in the first quadrant and the ordered pairs that go with them, I should know that one there. And if I know that one there, can I take both of those and reflect them on the x-axis? Yellow is not that great of a color here. I can't change it. Would you know then that those, if I understand this triangle is radical 2 over 2, radical 2 over 2, isn't that point right there going to have the same information? Radical 2 over 2, radical 2 over 2? Isn't that point going to have the same information? Isn't that point going to have the same information? Does that make sense to everybody? Same distances, because they're all 45, 45, 90 triangles with a radius of 1. However, because they terminate in different quadrants, the SIGN is going to be different in those quadrants, right? And that's what we've got to pay attention. That's the purpose of the reference angle, or the reference number. So my kind of task today and tomorrow is to get us to know what these 3 triangles in the first quadrant produce for us. They produce radical 3 over 2, 1/2. They'll produce a radical 2 over 2, radical 2 over 2, and then they'll produce a 1/2, radical 3 over 2. And then we can use that information to find all the other angles that we're interested in. So let me do something here real quick. Let's put the point, let's see here. Square 2 over 2, square root of 2 over 2. Put that point in. Let's put 1/2, square root of 3 over 2. Put that point in. All right, so bear with me. I know the graphics here are a little bit too big. Can everybody still see those if I make them that size? Okay. So those are the ordered pairs that get associated with those angles, okay, those triangles. And let me actually put in another one. Let's put in Q equals square root radical 3 over 2, 1/2. All right, so those 3 triangles, that one there, that one there, that one there, produce us enough information to find all these other angles in our unit circle. Is that okay with everyone? So let's do an example of this. Let's say that we're interested in finding T equaling, let's go, 5 pi over 3. T equals 5 pi over 3. And that is exactly the same thing as theta equaling 5 pi over 3, right? Now, what we have to do, we have to understand, where does 5 pi over 3 exist? Where does it show up in the unit circle, okay? If I have a denominator of 3, I'm going to write this as 3 pi over 3. I'm going to visualize that. And this over here is 6 pi over 3. Okay, if that's 3 pi over 3 and that's 6 pi over 3, doesn't this here have to be 4.5 pi over 3? Does that make sense? Now, you probably wouldn't traditionally use 4.5 in a fraction with 3 like that, but it's halfway between, 4.5 is halfway between 3 and 6, right? Okay, so where does it tell me what quadrant 5 pi over 3 is going to be in? It's going to be in the fourth quadrant. That's why I think it's important to maybe see that. So I know that 5 pi over 3 is going to be in the fourth quadrant. And if I draw out 5 pi over 3, we do see that indeed it is in the fourth quadrant. Okay? Now, so T would be that blue arc length, or it'd be this blue, theta would be this blue angle traced out. We want to figure out what is the ordered pair that goes with that point. Okay? So the first thing we have to do is figure out what T bar is, or theta bar. Okay, and that's how far I need to get back to the x-axis. That's why I wanted to know what quadrant I was in. Was I closer to the negative x-axis, or am I closer to the positive x-axis? I want to travel always the shortest distance. So which part of the axis do I go to? The positive one or the negative one here? Positive. Okay. So I know now that if I'm at 5 pi over 3, how far do I have to travel to get to 6 pi over 3? Pi over 3. Okay. So my reference angle, or my reference number, is pi over 3. So what I do is I go find the angle in the first quadrant that was pi over 3. It's this one here. Okay. That's pi over 3. This is pi over 4. This one here is pi over 6. So the reference angle, or reference number from the first quadrant, is pi over 3. And it has a terminal point of 1/2 radical 3 over 2, right? That's the terminal point right there of my reference angle. Okay, or my reference number. Now, looking back into the fourth quadrant, does that point A prime and the point N, are they reflections of one another? Does that make sense? You see all that? Okay, a lot of relationships here. They're reflections of one another. A prime is in the fourth quadrant. The x value has to be what kind of number in the fourth quadrant? Positive. The y coordinate has to be what kind of number? Negative. So now I've referenced and I know the numbers, I know the quantities, and now paying attention to the quadrant, I know that one's negative. And the nice thing now, we should eventually, as we work through this, the more you're exposed to this, the quicker you get at it. And you'll see eventually that when we say 5 pi over 3, you will automatically know 1/2 comma negative radical 3 over 2. It'll almost be as quick as saying, what's 4 times 5? Okay? That's kind of where we're trying to get with this stuff. Okay? So, again, if you took your calculator and typed in sine of 5 pi over 3, it's going to give you that negative radical 3 over 2. Does that make sense? Okay? If I typed in cosine of 5 pi over 3, it's going to give me that 1/2 for that x-coordinate, that terminal point. Is that something we can do? Okay. Now, as we work through this and practice this, a lot of the questions that we see are going to be, like I said, the multiples of pi over 12, and usually more like the multiples of pi over 6. Okay. So if I were to do, let's do just one more like that. Let's do, let's say t or theta is, let's go, let's go 7 pi over 6. Once you get a good hang of what you're doing, there's really not a whole lot of like examples that can be differentiated. And what I mean by that is they're not different. They're all very, very, very similar. Okay, we just found 5 pi over 3. Well, if I find 4 pi over 3, it's a very, very similar thing because it's the same reference angle, okay, a reference number. So let's try 7 pi over 6. 7 pi over 6, okay? What I like to do then, if that's 0, a distance of 0, this would be a distance of 6 pi over 6, right? So 7 pi over 6 is going to end up terminating in what quadrant? Third quadrant. Okay, so 7 pi over 6, kind of verify that. We do see that it ends in the third quadrant, right? Okay. So what then is the distance that I have to travel to get, the shortest distance I have to travel to get to the x-axis here from that point? I have to go there, wouldn't I? Does that make sense to everybody? That's the visual. How far is that? That's pi over 6. So my reference number or my reference angle is equal to pi over 6. Okay. Well, that means the terminal point for 7 pi over 6 is going to be the exact same thing as the terminal point for pi over 6. Terminal point for pi over 6 is that thing right there. So the terminal point for 7 pi over 6 is going to be radical 3 over 2, 1/2. Okay? But that's the terminal point for pi over 6. Terminal point for 7 pi over 6, what do I have to do to both those things? I have to negate both of them. Because the x and y values in the third quadrant are both negative. You're going to see me write this a lot. You're going to see this in our PDS and all that kind of stuff. Positive, positive. You'll see negative, positive. You'll see negative, negative, and positive, negative. So you'll see that image a lot. All they're talking about is the SIGN of the coordinates in those quadrants. Okay, which is something that obviously we know. We've seen that probably in Algebra 1 when they first introduced the coordinate system to us, but just kind of reintroducing that. Okay, so show you a couple here that my applet won't do right now. So we won't. Come on, whoa. I don't know what's going on. All right, it stops. All right, so let's do this. Let's do let's say our t value, theta value is, let's go negative 5 pi over 3. All right, so negative 5 pi. What's the negative tell me for that t value, that distance, or that angle? Say again? Clockwise. I'm going to go clockwise. Okay, I'm going that direction now around the circle. So going clockwise, kind of think about this. This would be 0. This is still 3 pi over 3, but if I go from 0 and I go that direction, maybe we view that as negative 3 pi over 3, right? This would be 4.5 pi over 3, right? This here will be 5 pi over 3. So I'm traveling around here. It's terrible. And I would get there. That would be the t value that we're interested in, right? Okay. Well, how far do I need to continue to go to get to the x-axis? Pi over 3. And they're going to ask this through WebAssign. You might say, well, I don't even need to know what the reference angle here is because I terminated on the first quadrant angle, right? Okay. But they're still going to ask you what t bar is, so it's still pi over 3. What is the terminal point for pi over 3? It's that there, right? Okay. So pi over 3 has the ordered pair of 1/2, radical 3 over 2. Okay, so negative 5 pi over 3 is going to have the exact same terminal point, right? Negative 5 pi over 3 terminates in what quadrant? First quadrant, so they're both positive, right? So that is referencing the exact same point, right? So that's my answer, 1/2, comma, radical 3/2. Another way of doing that, let's do a different one. Let's do let's say we go. Let's say t is -7 pi over 6. So -7 pi over 6. So this would be -6 pi over 6, right? All right. -7 pi over 6 is just a little bit further. This would be, so if this is 12 pi over 6, what's halfway between 6 and 12? 9, right? So this would be 9 pi over 6. So it tells you that you're existing there in that second quadrant. Okay, how far do I need to backtrack to get to the x-axis then if I trace out -7 pi over 6? Pi over 6. So this distance here is going to be t bar. Or if we're thinking about the angle, it's that angle right there, right? Okay, that angle ends up being theta bar, and you just told me it was pi over 6. Okay, so let's reference pi over 6. Pi over 6 is that coordinate right there, or that set of coordinates. So my terminal point is radical 3/2, comma 1/2. But if I have -7 pi over 6 terminates in the second quadrant, what do I have to do to these things? Make the first one negative. And now I've got the terminal point for -7 pi over 6. Okay? Let's do that one in an alternative way, because some people appreciate this or would like this better. If I know t or theta is -7 pi over 6, is that the same thing as, or would I get back to the same spot if I added 2 pi to that? So think about going -7 pi over 6. So I trace out -7 pi over 6. And that would be to there, right? So from that spot, add 2 pi. So adding 2 pi would be moving this direction again. Add 2 pi to it. Does it get you back to that same spot? Yes. So we talked previously about coterminal angles, right? Well, we can do the same thing with this distance and t. We can add one more kind of rotation back around that circumference. So if I add 2 pi to this, and I'm going to write it that way. Okay. So -7 pi over 6 plus 12 pi over 6, is that 5 pi over 6? So what we found out now is that -7 pi over 6 is the same thing as 5 pi over 6, right? So if you prefer to work with positive angles, you can now trace out 5 pi over 6. Now how far do I need to travel to get to there? Yeah, t bar or theta bar would still be pi over 6. If it's still pi over 6, I'd still pick out that angle there, or that ordered pair. And because I'm in the second quadrant, I still negate the first coordinate, right? Does that kind of make sense to everybody? Okay. Stop me if we're confused or something doesn't make sense. What I need you guys to do, and we'll spend a majority of tomorrow doing this, is we are going to need to memorize those pieces of information in the first quadrant. Now, I say memorize, and I use that loosely. I don't really want you to memorize. I think through exposure, it's going to be just trained in you or drilled into you what those values are. But understand the relationship. The relationship is that those come from the special right triangles, correct? Okay. If we understand that relationship, if we do memorize them and our memory fails us at some time, hopefully our background of knowing where they come from can kind of bring those values to the surface if we forget them. Okay? Because I want to give you quizzes at some point, basically kind of give you a heads up on what's going to happen here. I am going to give you something that looks like this picture here. And I'm going to white out every number on there. And I'm going to ask you to fill them in. Okay? But if we look at them and we understand the process that we just went through with the symmetry and all that kind of stuff, if you know the ones in the first quadrant, you know the ones in the second quadrant, don't you? If you know the ones in the second quadrant, you know the ones in the third one. You know the ones in the third one, you know the ones in the fourth one, just through symmetry. Okay? And the pi over 6, pi over 4, pi over 3, pi over 2, that kind of stuff, how to get those. Can you guys add, or can you count to 2 by 1? From 0 to 1, from 0 to 2, you can count there by 1s, right? Can you count from 0 to 2 by 4s? 1 fourth, 2 fourths, 3 fourths, 4 fourths, 5 fourths, 6 fourths, 7 fourths, 8 fourths? Can you count to 2 from 0 by 6s? 1 6, 2 6, 3 6, 4 6, 5 6, 6 6, 7 6, 8 6, 9 6, all the way to 12 6, right? You guys can do that. So that's how you generate then those angle measurements up there. And we'll talk about that. Spend a lot of time on that tomorrow. Okay. The one thing I want to talk about, because you're going to see it in tonight's homework, is a question that looks like this. They're asking you to find the reference angle if t equals 5.8. T equals 5.8. Now that's ugly, because it would be like saying find the reference angle if t was like 0.79. Well, that means at 0.79, I think, is about, or it is pi over 6. Okay, does that make sense? Okay, so when they give it to me this way, the pi has already been multiplied through. Is that all right, everybody? That's radians. The pi has already been multiplied through, which we see occasionally. It's not very often, but maybe once or twice in an assignment we'll see a radian written this way. Okay. Well, in addressing this and finding that we don't want to have an approximate answer here. We want an exact answer. If I think about 5.8, like I said, this would be 0. Obviously, pi, which you know is 3.14, right? You know this is 2 pi, which is 6.28, right? Or approximately. This would be 3 pi over 2, which if you calculate that, it's approximately 4.7. Hopefully that then opens your eyes to where 5.8 needs to reside. On the unit circle, 5.8 would stop probably maybe about right there, wouldn't it? Does that make sense to everybody? I don't know why it adds that little... Been doing that all day. There we go. So 5.8 would be about right there. So we need to figure out then what is, if t or theta is 5.80, what then is t bar or theta bar? What is this additional distance there? How would I find that green distance? Any ideas? Subtract what? Say it again. I think are you saying this? Or are you saying that? First one. Okay. So we want that first. We're going to take 2 pi, which is our total, subtract from it 5.8, and doesn't that then give me that little green distance? Okay. So there's my reference number. Okay. Now, if they wanted a terminal point that goes with that, we would have to know that from the first quadrant. So let's kind of do this. If I wanted the terminal point, okay, so I'm going to take 2 pi minus 5.8 gives me that number right there. Okay, I'm going to store that as x because I don't want to type it in over and over again here. But we've talked about how on the unit circle, that point right there has an ordered pair x comma y, right? Isn't the x value the cosine of that number? So if I type in cos, now I got to be in radians because that's what we've got here. So I am in radians. I got cosine of x would be that number there, 0.8855. And then the sine of x would be 0.4646. Okay. So then, so that's my reference point, right? Then the terminal point would be what? If this is the point in the first quadrant, and the terminal point is this one down here, what do I need to do with these numbers? Make the y1 negative. Okay. Now think about this. What is actually going on here? What do we just find here? We just found the cosine of 2 pi minus 5.8. It should spit back that 0.8855 number. And we just found then the sine of that 2 pi minus 5.8. It should spit back the 0.4646 number, but it should be negative. Okay. I'm sorry. Messed that up. I want the sine of 5.8. My apologies. 5.8. And the sine, or cosine of 5.8. So sine of 5.8 should give me that number there. And it does. Cosine of 5.8 gives me that x coordinate. Okay? But that's kind of where we're getting all these values from our calculator. Does that make sense? And what our calculator is trying to interpret for us. Now, our calculator actually generates them a different way. Our calculator generates the sine and cosine values that are popping up there from an algebraic principle. It's called a Taylor series. It's a graph that is approximating the unit circle for us. And it does a really, really, really good job of approximating. And it's easier to program the calculator with it that way. And I'll show you that when we start talking about the sine curve and cosine curve. You guys talking about that in physics at all? What did Natalie said they were studying it somewhere? Chem 2. Okay. Anybody in Chem 2 in here? Okay. So you might be dealing with the sine curve, cosine curve in there. If you know what that looks like, there's a Taylor series that we can use to model that very well that will actually do a better job of programming our calculator.
In terms of they would soon be learning it.
Okay. There is, I'm going to open up in the next couple minutes.